Okay, so welcome back. We're going to start today with the more theoretical part. So the idea is to have theorists and observational cosmologists together, exploring what can we learn from the new facilities. So it's a pleasure to have Diana López Nacir from University of Buenos Aires. She's going to talk about ultralight dark matter and observable phenomena. Thank you, Diana.
Thank you very much for having me here. Yes, hi. This is the topic. I'm theorist. So this is the outline of the talk. So after the motivations, I'd like to introduce these ultralight dark matter models. And then in particular, I would like to discuss first on cosmological perturbations, on properties on large scales. And in particular here, I will focus on some recent work I'm doing with mainly with one of my PhD students, Tomás Ferreira Chase, and also with Matías Belcerovich, another PhD student in Argentina of Susana Landau. Then I would like to focus on properties on small scales and some observable phenomena. And in particular, I refer to one recent work I've been doing on binary pulsars. So, well, so as motivation, as you know, the standard cosmological model, which is based on spatial isotropy and homogeneity, in addition to assuming the validity of general relativity. In this model requires the existence of dark contributions, and in particular, dark matter. In the standard model, dark matter is modeled as non-relativistic particles with negligible pressure. But there is a huge range of possible dark matter candidates. This picture illustrates, which I took from this paper. This illustrates the amount of different candidates. All these candidates, to describe the perturbations, they require different formalism. And the mass range is huge. It's about the order of magnitude. And for instance, the standard scenario, in the standard scenario, you model dark matter in terms of the distribution of particles, non-relativistic particles, so that when they are produced in the early universe, it's assumed that the number of particles is conserved. So the number density of particles and the energy densities, if they are non-relativistic, they decreases as 1/3 the volume. I am now focusing on an alternative scenario in which dark matter consists of ultralight bosons. In general, the standard candidates are axions, axion-like particles, or dilatons, but they can also be spin-1 vector fields or spin-2 tensors. The formalism here is different. And one observation is that since they are very light, the number of particles per unit volume is large. So there is a sense, a sensible description is in terms of the classical field. So I will use the classical field approximation. So just to present how we describe dark matter for this alternative scenario, let me start with the simplest case. This is spin-0 ultralight dark matter that is only interacting through gravity with the rest of the species. So at the background level, we assume Robertson-Walker metric. And in this background metric, this is the field equations you obtain from this action. So there are production mechanisms that happen during inflation for this kind of dark matter candidates. This production mechanism can lead to very homogeneous field, essentially a coherent classical field, very homogeneous. So you have that after the field is produced, you can write down this classical equation for at large scales, for the evolution of the field at large scales. And very early in the past, since H is large, H is much larger than the mass. So the last term in this equation can be neglected. And a constant is a solution of this equation. So this behaves essentially as dark energy. But once H falls below the mass, an approximate solution for this equation is given by this expression. So the field starts oscillating with a decaying amplitude. And if you compute the energy density and the pressure, you obtain this. So the energy density essentially decreases as for cold dark matter, as 1 over A cubed, 1 over the volume. But it has some oscillations on top of this. And the pressure oscillates with the large amplitude given by the energy density, and this oscillates with the frequencies twice the mass. But since H is much smaller in this regime than M, these are very fast oscillations. So on cosmological timescale, they essentially average to 0. So cosmological timescales are given by 1 over H. So it behaves essentially as dark matter, cold dark matter on the background level. And we can have essentially the same dynamics for spin 1 or spin 2 fields at late times once H is smaller than the mass. For instance, for spin 1, we can write down this action. This is the Broca action for a massive field. And if you compute the solution to the equations in a Robertson-Walker background, you have essentially the same result for the stress tensor. The only difference shows up in the anisotropic stress. So now, in addition to the pressure, this has a direction, the vector. So it has anisotropic stress. But again, the anisotropic stress is oscillating very fast. So on cosmological scales, this averages to 0. So you have essentially the same equation of the state, this effective fluid equations.
I always had a question about this, because it's a vector field at the background level that has a non-zero background expectation value in some sense, right?
Right, yes.
So does it break Lorentz invariance because it's a vector?
It breaks isotropy, and I will, yeah, it breaks isotropy, yes. Yes, actually. But it's on large scales, you can recover lambda CDM. This is a nice example. This is the example I will describe later in detail, also the perturbations. And the nice thing is that you recover lambda CDM at large scales, and you have a small anisotropic behavior at small scales. This is the result. But yeah, well, you can complicate even more the action and have essentially the same dynamics at short scale, from cosmological scales. For instance, you can write down a spin. You can consider dark matter to be a spin 2 field, a massive spin 2 field. It is in general non-trivial to write down a consistent theory for a massive spin 2 field on a curved space. But one possibility is, for instance, to construct this theory starting from a gauge-free biometric theory of gravity. In this theory, you have, in addition to the standard method to which matter is coupled to, this is the Lagrangian for matter, say in general, the matter is coupled to G, and you have an additional metric F, which has also the Einstein-Hilbert term, and this F is interacting through a potential term with the G metric. This potential term should have a special form in order to avoid ghosts in the theory. But you can start from this and you can do field redefinitions, assuming both metrics have the same background and that this alpha is very small. You can take this alpha as a perturbative parameter. You can recast the theory in this way. All the details are in this paper. And at the end, you have a massive eigenstate, this M, at quadratic level. This M can be interpreted as a dark matter field. And you have some interaction of this dark matter field with the standard matter that is suppressed by alpha. This is an universal interaction. This comes out from this construction. And the Einstein-Hilbert action is non-linear because you have to resample the perturbation of this G field to write the action in this way. So you can have a spin-2 field, massive spin-2 field on a curved background from the construction. So don't panic. This is the only. No, I will not complicate the things more. But I will go back later.
Can I ask a question about this?
Yes.
I thought that biometric theories had issues with perturbation.
Sorry, couldn't.
Sorry, I thought that with biometric theories had issues at the perturbation level. Instead that they were like forced or things like that.
At perturbation level.
Yeah.
At perturbation level, yeah, you have to impose constraints to avoid the gradient stabilities and yeah, so this velocity of scalar perturbations positive, but this will constrain the parameter space of your theory. But there is a region in the parameter space that.
Okay.
Yeah, but so again, at late times, on cosmological scale, once M is much larger than H, you have to solve this equation. And it's also, you have oscillations with a decaying amplitude and you compute the stress energy tensor, and the only difference is in the isotropic stress. So you have essentially the same background stress tensor. So one particular motivation, I think, to go and study fields with the spins are the results we already know about the evolution of the scalar case. Indeed, for the scalar ultralight matrix scenario, there are already public codes that are based on the standard Boltzmann codes, class or CAM. And using those codes, as you know, you can compute very useful quantities to make predictions in cosmology, such as the linear power spectrum. Indeed, this is the plot you can we made using the code developed by Breña López and González Morales. This is lambda CDM, the power spectrum for lambda CDM, the dashed black line, and the colored ones are for different masses of the dark matter field. This is the scalar case. So there is a characteristic suppression at small scales. The heavier the field is, the larger is the value of K for the characteristic suppression. So this is a particular property of this kind of dark matter. And one thing I would like to emphasize is all these observable properties that are strongly dependent on the value of the dark matter mass.
Sorry, why?
Yes.
So it behaves like whole dark matter, right?
Yeah.
So why there is a suppression if it's non-relativistic? These are non-relativistic particles, although it has small mass, it's non-relativistic, right?
At late times,
Or
there are some,
thermalized somehow.
no, they are not. They.
So that's not free streaming, and that's what I'm trying to say.
I will go into the details of the gene scale. This is you can analyze the gene mechanism. There is a particular scale. I will maybe, but not in the scalar case, the vector case, but it's analogous. Yeah, so, well, yeah, so to conclude, these codes are very useful to use also them as an output to compute even more observables, and to use precision cosmology to set constraints to these models. For instance, using lambda is using CMB and large-scale structure, already a linear scales, you can set a bound on the mass of this dark matter. And you can use those codes as input to Lyman alpha codes and then push this bound to heavier fields. So it's difficult to push the bounds for heavier fields because of nonlinearities, but this is possible to move on. So can we, one interesting question for me is can ultralight dark matter with different spins be distinguished on cosmological scales? So as the spin 2 case is too complicated, I will start with the spin 1. So our main goal is first to compute the perturbations with vector field dark matter. And the first difficulty, as Rogerio already mentioned, of having fields with the spins is that they break isotropy. So we will need to work on an isotropic background. And well, our final goal is to compute cosmological observables. So this defines the dynamics. So the dynamics is, you can write down an action, so it's not so complicated. You have the action for gravity, which we will assume it contains a cosmological constant. We have the action for the standard model, as for the ordinary matter, and this is the action for the dark matter. So as an isotropic background for the spin 1 case, we consider the Bianchi metric. The anisotropic part is characterized by the shear, which is the derivative of the special part of the metric, this shear tensor. For the standard model and lambda, we use the standard way of parameterizing using this equation of states. And for the vector field, then we need to solve the background field equations. The zero component satisfies a constraint equation, and the spatial components should satisfy this equation. And we can identify from the stress energy tensor of the vector field the corresponding energy density, pressure, and anisotropic stress. I will call this this way, which is the traceless part of the spatial part of the stress test. So I will assume there is a background vector field with a given direction, and that its energy density today accounts for the whole of dark matter. So this is the scenario. These equations are quite complicated, but we can solve them perturbatively in the shear, assuming the shear is much smaller than h. And this will be consistent, as I will show.
So this is your background, right?
Sorry?
This is background or perturbation?
So far background. I will analyze the perturbation afterwards. So for the background, this is the evolution of the magnitude of the vector field as a function of the scale factor. There is a particular moment at which the field starts presenting these oscillations. This moment I will call the oscillation time, and it's given when h is equal to the mass. So before this moment, the field increases as the scale factor, and after this, it decreases and oscillates. So for the energy density and pressure, it behaves essentially before the oscillation time, it behaves essentially as radiation, but radiation with an anisotropic stress. Okay? So, and after the field starts oscillating, the shear averages to zero, the pressure averages to zero, and behaves essentially as cold dark matter. Of course, to have for this field to be the whole of dark matter, we need this to start oscillating before equality, matter radiation equality, this vector radiation equality. vector radiation equality should be after, but this imposes a lower bound, which is quite weak. I mean, the mass should be larger than h at equality, which is 10 to the minus 28 dB. All right. So now we can use Einstein equations. From Einstein equation, we get the generalized Friedman equation, which now involves the shear, and the equation for the shear, which is sourced by the anisotropic stress of the vector field. We define the shear abundance in this way. And we can solve this equation assuming there is no initial anisotropy. We will consider that the only anisotropy is sourced by the vector field. So there is no primordial anisotropy. So if we set to 0 the shear at very early in time, at initial time, and we set the initial conditions early enough, we find that there is an attractor solution that is driven by the vector field and is given by this equation. So this is the attractor solution for the shear, and it is suppressed because this vector field, which plays the role of dark matter, is a dominant component with respect to radiation at this moment, very early in time, before the field starts oscillating. After the field starts oscillating, well, the source for the shear is vanishes. So the shear abundance evolves in this way. So this is the shear for different values of the mass. At early times, the shear is constant, and the lighter the field is, the higher is the value of the shear abundance. And already with this knowledge, we can set a bound on the mass, given that at BBN times, the abundance of the shear cannot be so large because otherwise the background will affect BBN observations, just the standard way of computing the Hilliard abundance, gamma equal h, will change because h changes. So using known bounds on BBN, we can obtain a lower bound on the mass. So, but well, we expect a stronger bounds on the mass coming from the analysis of perturbations. So the next step is to analyze perturbations.
So before I go to perturbations, today, would you expect the expansion rate of the universe to be different in different directions?
The shear abundance decreases very fast. So nowadays, no, unless for masses in this range, this will be completely negligible. Now we can speculate about the CMB quadruple and this kind of thing. This was analyzed already. But in order to have some shear abundance today that is relevant for the CMB quadruple, let's say, you have to have a very light field. And you expect this light field to be constrained by analytics.
I remember some people were doing studies of supernovas, measuring the expansion rate. But if you look at supernovas in one direction and supernovas in another direction, and see if there's any difference.
This is very interesting. That I will come to this in a few slides. Okay. Yeah. Yes.
I know that in inflation, in the concept of inflation, people look into these models with gauge fields to avoid anisotropies. It's based on SO3 gauge fields that is models by Malinejad and others.
Okay.
So I just wonder, because here you're going through these dangerous anisotropies because overimposed constraints. So perhaps if you, what will happen in those models where you can actually, if you just remove the anisotropies by this trick of working with gauge fields instead of just
yeah, there is a way of avoiding any anisotropy that is instead of starting with a background field pointing in a field direction, there is an isotropic state to begin with. But my point is that this kind of anisotropy is not so dangerous. And this on large scales, we will recover lambda CDM on large scales. On short scales, well, but you can constrain the model. But these short scales is more complicated. Yeah. Yeah.
Because my theory is very plastic. And if you have a vector field, I think you're only doing all this pattern within the RW. Should you do like Bianchi metric, something like that?
Yeah, this is like
Okay, I missed that. Okay. Sorry.
Don't worry. Well, so let's look at the perturbations. So first, I look at the scalar sector of the perturbation. So we split any quantity into background plus perturbations. This is the splitting for the vector field. So we perturb Einstein's equations. We use linear Rice equations. We did the calculation both in Newton gauge and synchronous gauge. I will show only the results on synchronous gauge, but we did both gauges because it's good to cross-check. And we defined an orthogonal basis using the background vector field. And so we needed to impose the initial conditions. And this is the main reason why we need to work on Bianchi space to set the correct initial conditions. Because at the beginning, you can think, well, this vector field during radiation domination is a subdominant component. So this will not affect the background evolution. Essentially, you will have an essentially Robertson-Walker space. But then if you want to impose the correct initial condition, you find that it's very difficult to impose, and you have some infrared problem here. I will show you this. So the idea is, as usual, you impose the initial conditions very early in time when the mode is outside the horizon during radiation domination. You impose that for all species. Delta rho or rho dot is the same, and we refer this to photons.
So
The one
adiabatic.
Adiabatic initial conditions, the standard ones. So as you might expect, the 0,0 component and the IJ component of Einstein's equation reduced to lambda CDM equations when the shear is neglected. Indeed, assuming this, which is true in this model, you can neglect them. And using this, plus the equations for radiation and following the famous Mann-Bertschinger paper, you can compute the initial condition for metric perturbations and for photons. But now, if you go and compute the I0 component of Einstein equations, it turns out that the shear, the part that contributes that is proportional to the shear, there's a term involving the shear that is the dominant contribution with respect to this for small values of K in the infrared. Introducing this here, you can see that this is of order K to the 4, but this is order K to the 2. And moreover, since you already know the initial condition from these equations, you replace this here and you see that the two green things cancel out. But this is in principle dominant with respect to this.
So is that first when we turn on the K squared term?
Sorry, I couldn't.
The first green box looks like K squared eta prime for mine.
It is K squared, but eta is a constant plus something order K. Yes. Yes, so and you can derive this just from these equations following Mann-Bertschinger. So, and these two things cancel out, and there is this thing that appears thanks to the fact that we are in Bianchi. If you would work from the very beginning in Robertson-Walker, you wouldn't have this term. However, when you compute the adiabatic initial condition for the vector field, you have that this term is order k squared. So if you work in Robertson Walker, you wouldn't have this, but you have this, that this is the dominant contribution. So you have a term that you don't know what to do with. But if you compute the correct initial conditions for the field, the adiabatic initial condition for the field, these two terms cancel out, so everything is consistent. So it's necessary to work in Bianchi background method to set the correct initial conditions.
Sorry.
Otherwise, you get the power spectrum at large scales not correct.
The red box also has the antler, right?
Sorry?
The red box also have the antler, and antler is for the T-score.
This has
You
eta,
cannot.
but this is the sigma is background. This is background. Yeah. Yeah,
So this is Bianchi one?
Bianchi one at the early times. So now we implemented the initial conditions and the equations in class code. And class, of course, it assumes isotropy. So it performs the evolution for all the equations for each value of k. We did the same, but now instead of doing once, we did this for each value of theta. Theta is the angle between the Fourier mode and the background field. So taking this as an additional parameter, you can evolve the modes for different values of theta. Okay? So for instance, in this way, we can compute it, the linear power spectrum for theta equals 0. That's for the longitudinal modes. So the linear power spectrum is similar to the scalar one. I mean, this is lambda CDM, and this is the linear power spectrum for the vector fields with longitudinal modes. And we obtain also a characteristic suppression at a given scale. This scale is known as the gene scale, and is given by this expression here. It has to do with this mass. And you can also derive this analytically by studying the gene mechanism. For the vector field, we obtain this equation. So you see if the mode has k larger than the gene k, it oscillates. I mean, this is the density constant for the vector field, which could be the dark matter. This oscillates like this green. This is the evolution of the density constant as a function of the scale factor for different modes. The green one has a k that is larger than the gene k, and the other ones are with k smaller than the gene k. So the green one departs from the lambda CDM. The dotted line is lambda CDM. So it starts oscillating, and this don't grow. This mode doesn't grow.
So, just a question. So you probably should have the perturbation delta A. You should have an index I for the component of the vector.
Yeah.
And then the power spectrum should have an IJ. Now we're taking the longitudinal one by fixing theta k equals 0.
Right.
What happens to the other components?
Yeah, I will show you now the other comparisons. We studied the power spectrum. The power spectrum now depends on this data. So we can plot different power spectrums, one for each data. And this is what happened for theta equals 0. But before going for the behavior for different values of theta, let me go into let me look into the gene scale a bit more, because this scale is very important in this kind of scenario. So this scale, it's constant. This is constant during radiation domination, and after equality, it grows. So a mode, I would like to notice the following. a given mode that is equal to that constant during radiation domination, that is a mode that is equal to the gene K in radiation domination, this mode enters the horizon when the field starts oscillating, exactly when the field starts oscillating. And you can demonstrate this in one line. So this is the condition for horizon crossing. I will call a star horizon crossing. And this is the condition for K equal to the gene K. So if you go put the square root to the other side, you can derive that this is equivalent to this. So, and this is the condition for the field to start oscillate. So the mode with K equal to the gene K is enters the horizon when the field starts oscillating. So A star is oscillating for this mode. And notice also that if this, since this is equal to this, K is equal to this, right? So this mode is on the border and the frontier of being relativistic or not relativistic. So modes with K smaller than the gene K enter the horizon being non-relativistic, but modes with K larger than the gene K enter the horizon being relativistic. So that's the reason. Yes, so this is now a plot for different values of theta. So this is for the orthogonal case, pi/2. The green one, the green dashed line, correspond to the scalar ultralight matter field with the same mass. This is for a particular value of the mass, but the gene K for this mass is given by the number in radiation domination. This is lambda CDM. And you see, this is the percentage difference between the different values of theta. This is computed between the orthogonal, for instance, and the theta equals 0. You have around the gene K more than 10% the difference. So it's quite large. So you can, I was surprised by this result. So it's quite large, the difference around the gene scale of 10%. So why? See, yeah.
Relates to what Roger said, I got confused with theta. So here you have different value for theta, but you could also have longitudinal modes and transverse modes.
Yeah, no, yeah. Theta tells you if the mode is longitudinal or not. Theta is the angle between. I will draw it.
So this is the angle between the anisotropy, the background.
Between K and A.
Yeah.
This is theta K.
A is background, right?
A is background. So now we have we are plotting the power spectrum for different K and theta K.
On top of that, you could also have longitudinal modes and transverse modes, because that's a definition that regards only to K, not to A. So or perhaps I'm not interpreting the situation correctly.
I mean, the longitudinal mode has K theta equals 0, and the orthogonal modes have theta equal pi/2.
I mean, I would say whether it's longitudinal or transverse has to do only with K. I mean, care about A, right? But now you have A on top of this, so
Well, I'm calling longitudinal just to the mode with theta equals 0.
okay.
Sorry, maybe
Okay.
not using the proper.
I think the confusion is that in this version, the power spectrum should depend on two angles, right? Because it's a vector, it's a unit vector on sky. So, and are you making the assumption that you have some residual isotropy in your space time, or it's in general?
I didn't follow. Sorry.
Because, for example, you have a vector type A and a free mole, right? But now that pick up the plane orthogonal to our vector A, this plane will be expanded in two independent directions.
Yes, there is
So
a.
there should be a dependence on azimuth of angle as well. This will answer your.
I think It's going
So
to
how children, the power spectrum is nothing from a vector K, and this vector has two components, the magnitude.
I see.
And the-
Yeah, so yeah, maybe you're confused because here I'm just studying the scalar sector of the theory. That's why. In general, in lambda CDM, scalar vector tensor, they evolve independently. I am here neglecting the vector and tensor modes, which in this case, they mix.
Yeah. So you're.
But we are
almost able to-
neglecting this mix, and this is a work in progress, the studying of the influence of the other modes. Yes.
Would this be show up in the ratio of the quadruple to one?
Yeah, of the CMP.
No, does it just publish power spectrum? They're looking for the redshift space distortion, and they calculate the quadrupole, which I think, and then, it's expanding in multiples of the percent.
So it's a comment, you know, or
It's a question with this, is this observable? This.
But if this is observable,
Yeah.
that's also, yeah, I expect it can be, but we need to, no, this
Because I think, if I understand correctly, you expand this, if you expand the power spectrum in say Legendre polynomials,
yeah.
then you'll get a P0 and a P2. P2 over P0 has been measured by
Mhm.
density, right?
Okay.
So it's a question.
Yes, I don't know. I mean,
Okay.
we need, yeah, I need to compute and compare with this. So far, we have this.
Okay.
Yeah, and well, I just wanted to understand from the evolution of the mode why this is so large in principle, and because probably, I don't know, we are making some numerical mistakes in the beginning. I mean, we are implementing the code, but we understand why. So
So I'm going to talk about what happens to those quantities when you increase the masses. Because I assume they are going to match the dashed line, which is the standard lambda CDM. But there are large amplitudes around for those curves. So I wonder if these amplitudes are going to shrink as well. So everything converges to the standard lambda CDM curve.
when the mass increases.
Yes.
I will show you this next. But first, I'd like to understand why this is happening. I like to understand why. I mean, so that's why in parallel we did all analytical approximations to, and the reason why this is so large is the evolution of relativistic modes when they enter the horizon before the field starts oscillating. And this is illustrated in this picture. So if K is larger than the gene K, this is all for a given mass. This is one particular example. If K is larger than the gene K, so the mode enters the horizon being relativistic and before the field starts oscillating. And we can study the dynamics here. And it turns out that the longitudinal modes grow much faster than the transversal mode. So any initial anisotropy is amplified between the time the mode enters the horizon until the field starts oscillating. Once the field starts oscillating, any anisotropy is erased. This is consistent with generic theorems. But if the mode is smaller than the gene K, this enters the horizon being non-relativistic. And it goes to the attractor solution lambda CDM. And this is the reason why we recover lambda CDM on large case. And this anisotropy is not so dangerous in this sense.
Sir, I don't think I understand. So the top panel corresponds to, on the left plot, the large scales, the low K, right?
A low K, yeah.
But you told us that there is a 10-20% difference in those low K modes. And now you seem to be saying there's no difference.
There is no difference if K is sufficiently small
but there is a difference on that plot, so which, at low K, you were emphasizing there's a 10 to 20% difference, right?
Yeah. You should see the other part of the plot. This is just a zoom around the gene scale.
So maybe
So
the 10%
that's
difference is around close to KJ, right?
Yeah, it's close
So
to the
it's
gene scale.
intermediate, so that is
Okay,
extreme
so
back to the.
okay, so the reason for the 10 to 20% difference is it's in some transition region between the large KMOs that are oscillating a lot, that are very dependent on the angle, and low KMOs that are independent of the angle.
Yeah, this is for very small case.
The lower left plot, you have, I can see like 3 or 4 colored lines. Do
Yes.
those converge as you move to the left? Do they go to the same thing? if you move
Yeah,
to the
they go to the same thing. Maybe, yeah, this is because just to amplify, I took a very light field, but if you can also do the same for this is the same plot, but for different masses, heavier fields. You see that here, this converge. I mean, this is the percentage difference. It goes to very small values, but near the gene K, you can get about the 10%, regardless of the value of the mass. This happens near the gene K. So for even if the mass is small, the smaller the larger the mass is, the higher the K at which this difference happens is. So make me explain myself here. But this is something that happens near the GK. So you have to see this separation at gene scale, and this separation in the vector case, it is anisotropic. This is the main difference we identify with respect to the scalar case. The scalar case has also this separation. These are percentage difference. This is the orthogonal theta equal pi/2 with respect to the longitudinal one. So you have this 10% around the gene K. This is the percentage difference of the longitudinal with lambda CDM. So at gene K, the difference is quite large. And this is with respect to the scalar case. So there is a difference also with respect to the scalar field. For different values of the mass. So the color is for each color is for one mass. These are lighter masses and heavier masses. So it would be great to use this, I think, to use this as an input on numerical simulation and see what happens with the structure formation. If there is some imprint of this anisotropic behavior in structure formation or not. But this is something that I think is worth doing. But we need to work on this. So now let's change a bit the topic. I don't know, I am going with the time. But I would like now to focus on small scales. Since for vector fields, this is something to be done. I will focus here on scalar ultralight dark matter. So for scalar ultralight dark matter, there are already numerical simulations of structure formation, and the first done by these authors. So for instance, you can consider a halo, a virialized halo, as is made of a superposition of waves with random phases. So this superposition produces in a space interference patterns that are characterized by some wave package with characteristic size of order of the de Broglie wavelength. And you can estimate the value of the typical de Broglie wavelengths using the typical velocity for the virial halo, our halo, say, and a typical value of the mass given by this value, say. And So when due to the motion now of the wave packets, at a given point in space, the field will lose coherence by a time that is you can estimate as the time, the crossing time, the time is the half of the de Broglie wavelength, which is the size of the wave package, divided the typical velocity. So this
is a
will be
quantum
the
effect.
coherent time.
That's a quantum effect. So that's because
Quantum
particles
is
are
because we have the mass, and the mass has units. It's a
because
classical
it's very
field.
light. It's a classical.
Yeah, it's a classical field, but it has a mass, so there is a quantum time.
But the
There is such is
Broglie
variable.
wavelength is something in quantum. No,
Yes, you can think it is a quantum in terms of particles. Yeah, but it's a classical field approximation, and inside each coherent patch, the field, the classical field, oscillates, and it has oscillations that can be described in this way with a given amplitude and phase, and the amplitude and phase depend on which patch, which coherence, on each coherent patch you are. And all this is dynamical. So in a given homogeneous patch, you can see the field evolving. So if you observe the field for a long time, longer than the coherent time, you would see something like this. But if you observe the system only for a short time, smaller than the coherent time, you would observe a monochromatic wave. But the amplitude of this monochromatic wave will depend on which time interval you choose. So the conclusion is you don't know how to model the local amplitude of the field. You have a classical field, but you don't know how to model the local amplitude of the field because it will depend on when you start. So even if you observe a very short term, what you can model, and this is nicely described in this paper, you can model the amplitude PDF. So you can model stochastically the classical field in this way. So on average, it gives the energy density of the halo, this rho, the halo, but the amplitude, you can model the PDF, and it's given by this Rayleigh distribution. And the phase is identically distributed between 0 to pi. It's a random phase.
So the origin of stochasticity is what? Some fluctuation?
It's a way of characterizing your ignorance about the local value of the amplitude of the field. You don't know if you're here, but as long. And for instance, I'm focusing on partial time in observations, and partial time in observation are for times that are shorter than the coherent time. So you are in one of these chunks, but you don't know which one. So to characterize your uncertainty, your ignorance about the local fields, you can use this distribution. And I was very happy when I realized that defining these variables, you can turn this distribution into a Gaussian. This simplified me a lot the calculations. I was very happy because you just use the cosine, you split the cosine into cosine and sine, and then it's equivalent to say that R is taken from this distribution and the phase is random, then X and Y, these amplitudes, are taken from this Gaussian.
The coherence time is related to the mass of the field.
The coherence time is related to the mass, and in the case of the halo, the typical velocity, the halo. And it's about 65 years for this value of the mass.
They were really wavelength is about kiloparsec, megaparsec, which is the scale.
Yeah, in parsecs.
No, astronomical units.
Yes, large. Yeah,
It's huge.
Yeah, it's huge. Big galactic, but it depends on the mass. Yes.
And this is just a scalar
This is
field
smaller.
with a potential that's periodic or
Sorry?
quadratic. This is just a scalar field.
With the mass, yes, quadratic, yeah.
Just that.
Yes, just that. It would be great to have the same description, phenomenological description for spin 1 and 2. And this is, there are some work doing in this paper, but this is still underdeveloped. So, well, there are several observables that have been identified to prove that can constrain this kind of field or test for different values of the mass. For smaller fields, you can use CMB or large scale structure or large scales, as I mentioned. Then, if you implement this to push the bound towards heavier fields, you need to go nonlinear principle to implement to study Lyman alpha forest, for instance, galaxy formation, the structure of galactic halos, so on. But so, as I would like to emphasize, as you know, robustness depends on the observable, theoretical uncertainties, and modeling. So in this scenario, it's important to have complementary observations, complementary proofs for the same mass ranges. And that's why I'm focusing on this, binary pulsars and pulsars in general. And of course, all of this, as Rogerio mentioned, can prove ultralight dark matter interacting only through gravity. And if you assume that ultralight dark matter is directly coupled to a standard model, there are many other proposals, such as using atomic clocks, accelerometers, resonant mass detector, laser atom interferometry, and so on. So very briefly, I would like to comment on my work on pulsars. So first, why are we considering pulsars? What is pulsar? I don't know if you are all familiar with this. A pulsar is a neutron star that is fastly spinning and emits in radio along the magnetic poles. And as it is fastly spinning, when you see this from Earth, it acts as a radio house instead of a lighthouse. It's a radio house, and you can time the time of arrival of those pulses from Earth. And pulsar timing techniques are very precise nowadays. This is in this plot, each point represents a pulsar, and those with the red pink circle are in binary systems. For instance, this is the famous Hals-Taylor, from which you can infer the existence of gravitational waves at first time. These systems are very useful to test modified gravity theories, the presence of gravitational waves, and in our case, we use them as potential detectors of ultralight dark matter. So how would ultralight dark matter affect pulsar timing? So I don't have time to go on this, but these authors were the first noticing that if you have the halo, the dark matter halo, the time scale for oscillations now is relevant because it can be 100 days. It's relevant for studies inside the halo, and this halo source gravity, acts as a source of gravity, and these oscillations in the pressure can cause oscillations in the local metric field. So you have, if you solve the instance equation, you have like a standing wave. This source standing wave, in this case, is scalar standing wave that is oscillating with a frequency that is twice the mass. So this is these oscillations that will affect the systems, and they computed how these affect the pulsar timing arrays observations. And the result is essentially the same. as having a scalar gravitational wave with this amplitude. So you can do forecast and constraint. So this is the expected signal, and this is the forecast to put bounds on this characteristic amplitude. And this also can be computed for spin 1, and we did the for spin 2 too. Well, but recently, these authors, using the second data release of the European pulsar timing array, they show that these observations are very good for constraining ultralight dark matter. Actually, they were able to rule out that all the dark matter can be made, rule out this mass range. At least not all the dark matter can be made of this kind of ultralight dark matter with this mass. So they put a bound on the fraction of dark matter made of this kind of scalar field for this mass range. So this shows the potentiality of this kind of observations. Well, for spin 2, you can also work out the thing. The good thing is that this signal is quadrupolar, so it's in principle simple to discriminate the signal using the correlate, using that this can be, for instance, the typical error or clock time standard is a monopolar, or an error in the planetary ephemeris is dipolar, and this signal is quadrupolar. So maybe you can this can help to put constraints. But very fastly, so I'm now focusing on binary pulsars, not on on this pulsar timing array. But for binary pulsars, there is another effect of the ultralight dark matter field that is useful to put constraints for a bit for heavier fields. And just I'm going fast because of the time, but so if I can take some more minutes. So otherwise stop me, please. So binary pulsars. So let's take a look at some numbers. We can estimate the typical size of these systems using Newton's law, Kepler's law, and the typical orbital periods. This PV is the orbital period of the system. Typical orbital periods are of order hours or days, 100 days. So this is one of the largest distances. So this distance is very small with respect to the typical coherence length of the fields I will consider. I will consider heavier fields, but not so heavier, much larger than 10 to the minus 18 eV, because for heavier than this, we need to include the back reaction of the binary system on the field, and I will neglect that. But you see the field can be assumed to be homogeneous on these length scales, and coherent, because observations of pulsar timing observation are on smaller time than the coherent time. And the oscillation time is relevant, so can be of the same order as the orbital period. So, and there are very precise measurements for binary pulsars that allow to extract the values of the orbital parameters for the binary. Actually, immediately after the discovery of the Hals-Taylor pulsar, binary pulsar, these people developed a model to fit data, and this model also includes some phenomenological ways of parameterizing deviation of the orbital parameters, some secular variation of the orbital parameters. And you can fit for this and extract this information, the secular variation of orbital parameters. And dark matter oscillates, and this is like a force that affect this orbital motion of the binary system, either because it produces an oscillating local metric, or because it's directly coupled to the stars. Because if it is directly coupled to the stars, it oscillates. The oscillations affect the Keplerian motion. The Keplerian motion can be decomposed in Fourier series. These are the harmonics of the orbital period. So this is the Kepler solution, the Ampere solution. And so, in principle, these two are of the same order, so there can be resonances. And if there are resonances, for instance, one can compute that there is a secular drift of some orbital parameters. For instance, the orbital period will change in this way. So the dark matter will produce a secular variation in the orbital period at resonance. So since if you don't see any secular variation, any anomalous secular variation in the orbital period, you can put a bound on the density of dark matter or the coupling constants of dark matter to the stars. And this is something that we have done in the past. Assuming resonances, we have put constraints on masses and coupling constants or for spin 1, 0, and 2 in these papers. But my recent result is not for only for the resonant cases, but we went a bit beyond resonance. So this is what I wanted to tell you about this is the news, the good the new thing. So to illustrate this very fast, I consider a specific example. Now, these binary pulsars, unfortunately, the sensitivity is not so good to constrain the pure gravity interaction. But if we assume a direct interaction between the stars, the neutron stars, and this dark matter, for instance, through an universal coupling like this, we can constrain the coupling constant. So you can constrain this coupling constant. Hopefully, this can improve until we can also constrain pure gravity interaction, what would be the best. But let me just illustrate this. So since now the dark matter is directly coupled to the stars, basically this coupling produce a change in the mass of each of the binary members, and you obtain the Newtonian problem perturbed by a characteristic force that depends on this dark matter, and this oscillates. So we use a Bayesian approach now to estimate the bounds, to construct what is called the sensitivity curve for the coupling constant. Basically, we have two competing hypotheses. In one is that there is no dark matter, so after subtracting all the known effects, you are left with noise. This is what we call the noise hypothesis. And the ultralight dark matter hypothesis, in which on top of the noise, you have the dark matter signal. So the log likelihood of this of the signal hypothesis will depend on some nuisance parameters and the parameters of the dark matter, the local dark matter field, which is the X and Y are the local amplitude of the sine and cosine for this dark matter wave, and the mass. So we told us just to construct the sensitivity curve, we follow literature that have been done this for gravitational waves. This is analogous. And what we have done was to estimate the base factor. This is, we took the ratio between the evidences, the marginalized likelihood, taking into account the priors. And this will depend on fiducial values of the dark matter parameters. We don't know the local values of the dark matter parameters, but we can we know the PDF for them. And now in this formalism, we can also combine different systems, different binary systems. This is for one binary pulsar, but if we have M systems, we can combine them. And we can define a threshold for detection. We follow the liter, we put a very stringent threshold for detection, and setting this equal to this, we get the sensitivity curves. For instance, this is the sensitivity curve for this coupling constant alpha. These are solar system bounds, so we are almost there. And these are the resonant peaks. So this system resonates. This is an eccentric system. It resonates with the binary. And so we can recover with this method the limits we put before at resonance, assuming resonance, but we can go beyond resonance. So what we need here are the binary parameters, the observation parameters, the noise sensitivity, the noise in the timing, the rate, U time, and the amount of years. This is smaller than the coherent time. They used nanograph systems here. And the dark matter parameters.
How many
Yes.
systems you have? How many binaries?
Here is only one.
That's
This plot is for only one.
we can improve.
But we have many curves because we don't know the local value of the dark matter field. So what we can do, we can randomly take these values from the corresponding distributions, and so we can draw different sensitivity curves. According, so we just randomly generate this, so that's why we have many. So instead of having one sensitivity curve, because in order to characterize this ignorance, we draw many. So we have a band there.
But you have more systems now also.
Yeah, now we can apply this to more systems, and we can combine. We have, this is the same plot for the other different systems, and now we can also combine them. I have, yeah, they have many peaks because.
Where is the solar system found?
The solar system is around this.
Okay. So it's still not there.
It's still not there. No, Cassini has made a very good job. But the main problem here is that we don't have many systems in nature that are very eccentric, and systems that have almost near circular orbits do not resonate with a scalar field. But now, with this new method, we can go beyond resonance, and we can also use almost near circular systems or near circular orbits. So in this plot, we have the bounds. We obtain the sensitivity curve. We obtain using 20 systems. This ELL1 stands for systems that have almost circular orbits. So we need to model differently the motion. And this black line band actually is a band because we do this for random realizations of the local dark matter field. Correspond to conductivity curves computed using orbital period or the major axis, how dark matter affects this. And the orange one is using this other orbital parameter, which has to do with the time of ascending node. Well, yeah, I'm finishing, yes. So still not as good as Cassini. These are the bounds for light and field obtained using the partial timing array I mentioned before. But we can also test this ratio. And we can do forecast. So assuming some parameters that we took from forecast for SKA, for instance, we can go a bit below, but it's complementary for this. And so then just conclusions. Sorry. Regarding to the early time evolution, we noticed that the scalar dark matter behaves as an isotropic dark energy, but vector field requires this anisotropic shear because to work in a Bianchi metric, and already we can set bounds using BBN. For smaller scales, we have this suppression effect at chin scale. For the scalar, we have a suppression, the same suppression for any direction, but for the vector field, the amplitude of the suppression will depend on the direction of the Fourier mode and the vector field. Beyond the linear regime, well, constraints are sensitive to uncertainties in modeling, so it's crucial to have complementary proofs and independent proofs. And so why? Because we are working also with pulsars, and well, these phenomenological descriptions on the small scales are necessary because not only to analyze the pulsars, but also local laboratory experiments that are proposed and going. Well, these are to do for my conclusions for partial timing. These are useful to prove ultralight. So I leave you with some lines of ideas for future work we will working on. Thanks a lot.
Thank you, Jenna, for the 4 or 5 talks that gave you. More questions for Jenna?
Again, thanks for the talk. So can you come back to that slide about the vector field where we compare the results from scalar field and different theta's as well? There's like a 2 columns, a couple of rows. Yes, that's one. So in the top left, you are comparing the scalar field with the vector field at theta equals 0. So as I read it, you do have some differences, right? Even at a really small case, right? So you could differentiate between a scalar field and a vector field, right?
Yeah, a small scale you have, yeah, depending on the mass, yes.
Yes, depends. So you put some constraints on the mass
Yeah.
of your vector field, right?
Yeah.
That's observable.
The first thing we are working on is we want to compute a CMB power spectrum. This is something we are doing these days because to compute and to see whether we can obtain different constraints on the vectors than for scale.
And the second question is, you are assuming that talking about the background vector field now. So you're assuming that we live in a huge domain where everywhere in the observable universe, the vector field points out to one direction only.
Yeah.
So so the question is twofold actually. So as far as I can remember, the amplitude of this vector field is going to decrease really fast with the expansion of the universe. So the constraints are going to be really harder and harder to get because the amplitude is going to be really small. And the second question is, why can't we think that the universe has like smaller domains where the vector field points out in one direction each of these domains, so as in the large picture, you don't break isotropy?
To the first question, I mean, the amplitude of these fields, these vector fields, I mean, it's not decreasing. It's
The expansion of the universe.
but it is decreasing, but it's decreasing as a matter after the field starts oscillating and before as
Because it, yeah.
as radiation. So at the background level, we have this evolution. So we fix the conditions so that this is the account for the whole dark matter today.
Oh, okay.
So, and it behaves as dark matter until the field starts oscillating, going back in time, and then as radiation, but with anisotropic stress.
It may be confusing with vector perturbation.
Vector perturbation, yeah, vector perturbations. We already made progress on that. Vector and tensor perturbations are not giving any.
Okay. What about the
Big.
second question about the domains, different domains, where the field would point out to one direction in each domain? There would be some constraints perhaps on the interface or.
Yeah, what people is doing now is they are considering different initial conditions. In particular, in this paper, it's ICTP paper. Here, they are doing simulation of halos. For instance, if you have some halo where the local polarization of the field is in one direction, another direction, what happens when you have for equipartition of energy where this polarization, how to model at small scale the polarization of the field. Field is polarized, it's elliptically polarized, or at small scale, what happens? This is interesting.
That reference.
Yeah, but I think one thing is that is to be done yet is to use the output of this class, this linear power spectrum as an input of numerical simulation. This would be interesting. See consequences in structural information. But Diana,
I'm sorry.
Yeah,
yeah.
No, if you.
This output that you get from GAM, if I understand correctly, you are using just the linear power spectrum, is that correct?
Yes.
And so I guess that for the structure formation, if you want to input this and also considering the scale you show, you may need the non-linear power spectrum. Have you include this effect in the non-linear prediction?
This is to be done. Now we need to work out the initial conditions, the proper initial conditions, because now they are isotropic, so we need to extend this generation to generate the correct initial conditions for remote simulations. Then also to do the remote simulations is quite expensive. Yeah, this is something interesting, I think. But we
Gonzalo?
So I'm probably wrong about this, but I would have thought that by having this background vector field, the fluctuations, the perturbations, the scalar and the vector fluctuations will couple at the linear level. But it won't be easy to decouple them as in the usual scalar vector tensor composition, right? What I understood is that you just evolve them independently, like scalar fields, scalar fluctuations evolve just by itself, even with this background.
Yeah, what we have done, we have neglected the vector and tensor perturbation, the mixing with the vector and
But they will
tensor.
mix, right?
They will mix in general.
That's effect.
This is a work in progress, but according to some analytical estimates, our conclusion that they will not make the difference.
At every scale or they will not be important at large scales as you already.
For cosmological perturbations.
Yeah.
At least initially, we compute at the initial conditions, they decouple effectively. Because the shear is very small with respect to age. We're working always perturbatively in the shear, the northern in the shear.
Okay, but even at
This is
linear
the
level,
very
they would be coupled.
Sorry, again,
At linear level, they will be coupled anyway.
Yeah.
But you're neglecting the effect, which is,
Yeah. I am neglecting this effect. Yeah, I think Thomas has all the equations, but so we can work and implement them in class, but before we are trying to see whether it's worth spend time doing this.
Okay, so as usual, we're running very, very late. I want to remind you that the next week there's going to be a talk on pulsar timing arrays. So it'll be interesting to discuss whether you can distinguish these signals in pulsar timing arrays from stochastic gravitational waves, things like that. So that can be a discussion for next week. So let's thank Diana again. Well, if they come back 11:45.